The thing about the refrigeration basics, going over the circuit, is that there are layers to this this fundamentals of HVAC that you can go deeper and deeper and deeper that help you in every aspect of your diagnostic and understanding of this. So for me, I got the refrigerant circuit memorized. I had the line names memorized and their basic function memorized within the first month. And you could ask me a question, I would spit out my memorized answer. But I didn't know how to use that information to solve problems, until a few months after that. And then once I was in my own vehicle about a year in, I probably got stuck for about 2 years with just enough knowledge, kind of rule of thumb type stuff, using what I knew of the refrigerant circuit and then what I knew from experience or calling somebody for tech support to solve problems. And then somewhere around year 2, I went back. Brian started doing podcasts, started making videos, went back to looking at the fundamentals again. And my mind was just blown. It's so much deeper, it's so important. There's a lot of layers here that can help me understand what I'm doing. And once you get that understanding, you can get a phone call from somebody. They give you a couple pressures, a couple temperatures, and immediately you can picture what's going on in the system. And something they haven't even checked yet, you can tell them to go look for. Because the refrigerant circuit is this piece of cool science and chemistry that just it is a balanced system. Everything affects everything in it. So once you have a deep understanding of it, you can get a few points, temperatures, pressures, whatever it is, and then understand what's going on in that whole circuit, what to look for. So the other thing I wanted to say is that at Kalos, we absolutely celebrate guys coming in that don't know anything, experienced techs coming in that don't know what they should, and people from maybe an install. You've been on install for 8 months. There's not a lot of opportunity to do diagnostic and learn, depth stuff on the install. You're typically hands-on, just putting stuff together. Charlie's got less experience, but he probably knows a lot more about refrigerant than you do. And so we have to come into this classroom, lay aside our ego completely, and I want you guys to know that the person who asks questions because they don't know demonstrates that they're not understanding it, they're not figuring it out, and is willing to say, you just explained that twice, but do it a third time. Those are where the points are today. You're the guy that's going to have the points. We don't want anybody left behind. I don't really care if everybody in the class doesn't make it all the way through this slide. If we leave a couple of you behind because you're nervous to speak up, you're like, dude, I'm already in a van, I shouldn't be asking this question. There is no I shouldn't be. Maybe it's true. Maybe you should already know it. I don't really care. All we want to do is teach it if you don't know it. So if it's confusing, it doesn't make sense, or you disagree, speak up, be engaged. And that's part of my role here today. So Elliot took the lead on this. He was doing some teaching in the van, and he was like, there's actually a lot of confusion with some of the new guys on this stuff. Let's put together a slide. Let's go back to the very basics, absolute basics. We're going to start with what is pressure, and we're going to build on that and go all the way to hands-on diagnostic, creating problems on our unit before we leave today.
So we're going to try and keep this practical. There's a lot of sciencey stuff behind this that is not useful in the field, right? I'm sure you guys have heard Brian's podcast, and he can get way deep and talking about this stuff, and it goes over my head, right? Because I don't understand the ins and outs of every law of thermodynamics and stuff. But there's a lot of practical things we can take away from just the very basics that will help us in our diagnostics when we understand what are terms like superheat, subcool, what are the pressures actually telling us about our system. You can start to picture it in your mind and see what he was talking about how this whole system is one thing, every little piece affects something, and you can see it in your readings.
And you end up enjoying your job way more.
Yeah, for sure.
When you don't get stuck just following rules of thumb and calling for support.
Yeah.
When you actually understand it, it's like all of a sudden what you did yesterday is way more fun today. Yeah.
And customers will think you're crazy because when you find a low voltage short, you'll be like, oh, cool, problem. Yeah. So so these are the 4 main components of our refrigeration circuit. Does anybody not know the names of all 4 of these components? So everybody knows what these are? Okay, who wants to name them for me? Alfonso, go ahead.
We have our compressor, condenser, thermal expansion valve, and our evaporator coil.
Cool, awesome. So those are the 4 main components of our refrigeration circuit. And you want to describe the flow for me too, or?
Yeah, and the standard
Yeah.
high pressure, high temperature liquid passes through the condenser, turns into a high pressure, high temperature.
You got lost.
Yep.
Start at a component instead of a refrigerant.
Vapor.
Alright, start at a component. Which one do you want to pick?
I always start at the compressor because that's like the heart of the system. So,
Okay, the compressor turns the refrigerant into a high pressure, high temperature vapor, passes through the condenser, turns it into a high pressure, high temperature liquid, passes through the thermal expansion valve, drops the pressure to a low pressure, low temperature liquid, and then goes to the evaporator coil, pulls in the air from the indoor area, and then it turns into a low pressure, low temperature vapor.
cool. The only thing I want to say is, this is technically not a liquid in the same sense that this is a liquid. So when we're,
Saturated.
yeah, there we go. I'll take that.
Even though it's 98% liquid, still,
Still.
it's changing state.
So those are the 4 main components. You will see these in every refrigeration system. Even you guys that are in commercial, if you ever get into like rack refrigeration, the components are still the same. There's more bells and whistles because there's a lot more regulation that goes on there, but there is no HVAC system that does not work without these. But
Who here would have struggled to give the same description Alfonso just did? Right on. Okay. Alright,
I'm gonna fix that.
that's good. That's good. That's why we're here today.
Yeah.
And so, there's so much more than what Alfonso said to that circuit too, that you could go in with each one of those steps, lines, process, and depth. But that basic outline he did was a memorization process. So that part, you can take a picture like this from HVAC school and just memorize that in your head so that that description can come out whether you understand it or not. And the reason that helps you is because then the language is in you. So as you're learning things and listening to people ask questions, calling for tech support, whatever it is, if that language is memorized, then when they give you information, it goes into its proper spot. Like, okay, yeah, that's right, that's the compressor. And after the compressor, the discharge comes out. So it's okay to memorize at first before you understand. It will help you, but yeah.
Yeah, communication. One of the things you'll find is when you ride with different people, they'll call the same thing by different names. So there's like, for example, when we were talking about, you said a liquid, and I said be more specific, a saturated liquid. Okay, cool. That's also called a boiling refrigerant. I've also heard it called a flash gas. I've also heard it called a, what else? Did you get another name?
For what?
For
I wasn't listening.
Okay. Yeah, basically, so, and they'll call it by different names. So by knowing all the different names that techs will call it by, you'll be able to communicate better. But that is a basic overview of it. Very nicely done. And hopefully everybody will be able to give me that by the time we're done here. So we'll start at the beginning with pressure. So pressure is the force on something, right? So and when we're talking about pressure in the field, right, we're using probes and we're trying to measure what is the pressure of the refrigerant on its container, right, on the copper tubing. So there's a couple different kinds, right? We've got pressure that's gauge pressure, which is what you're going to read with your manifold gauge, with your field piece probes. There's also something called absolute pressure, which is you might see in manuals sometimes because that's what labs use. So the difference is that your gauge pressure takes into account already atmospheric pressure. So atmospheric pressure is 14.7 PSI. That's how much the air on us right now here at sea level weighs, or how much pressure it exerts, right? So when we're talking about gauge pressure, our gauges are already in atmosphere, right? So when they're reading 0, it's actually 14.7 PSI. But in lab conditions, when they do testing, they use a different scale. They use PSIA, which is absolute, which does not take into account that atmospheric pressure. So it's, for our purposes, it's not really important. We're never going to use that in the field. We're always going to use PSIG. Because that's what everybody's in atmosphere, right? That's just the ground level that we start at.
If you were to go and look up a PT chart, let's say you're like, okay, I need to look up a PT chart for this refrigerant, find out what pressure this refrigerant is at this temperature. You want to see at the top of the chart, it'll typically say PSIG or PSIA. So that's where it can come in and bite you, is if you're going off of a chart that you went and looked up online, it could be an technically accurate chart, which would be PSIA, and then when they say 14 PSI, they actually mean 0 PSI for your gauges. So that's and then the other time that you'll use it is if you're trying to ever look up the ratio for a compressor, how to find out what a compressor's ratio is, then they use atmosphere pressure to do that calculation for some reason. I don't know why, but they always do. The thing to know about it is that we live at the bottom of an ocean of air here at sea level, so we are living with constant pressure pushing in all around us, holding us in place, keeping our atmosphere where it should be for life to exist. And we are living in 14 pounds of pressure per square inch. What's PSI? Is that square inch? Pounds per square inch, yeah. So we're living at 14 pounds per square inch constantly. So we are pressurized systems, and our atmosphere is pressurized systems. And the gauges just start at 0. They don't show that we're living in 14 PSI, because practically in life, when we go to add refrigerant, we need to know how much above what we're living in are we working with. We don't
like the difference.
Yeah. Whereas if you were to remove the 14 PSI, what state would our world be in? What would happen to your bodies? What would happen to our world if we were to take away the 14 PSI?
Probably float. But
Float? No, we wouldn't. Gravity holds us down.
Would it be like in space?
Exactly right. That's what space is.
Boom.
So you jump out of the spaceship and instantly boil, freeze, yeah,
And explode.
and explode. It's because it is a vacuum. So when we're pulling a vacuum on a system, we're going below 0 PSI, but we're still actually under some sort of pressure. We never pull an actual vacuum. We're just going lower than the 14 PSI, which is, takes equipment to actually produce. But yeah, that's what space is. That's what makes space dangerous to us humans. It's a vacuum. It's what we call a vacuum, but it just means it's not pressurized.
So there's a couple little fun apps that we'll probably talk about today. One of them is the Danfoss refrigerant slider tool. It's this red one here. So that's like, it's a refrigerant slider. It's kind of like it's a PT chart app, but on it you can toggle your gauge pressure or your absolute pressure if you're curious about what that looks like. But that's a fun one that I use sometimes when I'm trying to figure out. I want a quick PT
Which one is
chart.
it?
Huh? The
Rev
Danfoss, yeah, Danfoss Rev Tools. I keep that one.
Bro, I already had it.
You already had it?
showed it to me.
Well, I've showed it, if you've been in my van, I might have shown it to you.
yeah,
But yeah, so even a vacuum that we pull is still under pressure, right? But the thing is, we use different units to measure our pressure. So when we talk about refrigerant pressure, we're dealing in PSI, right? Because that's the most useful scale. But when we're doing a vacuum, we don't use PSI, right? What do we measure a vacuum in? Who can tell me?
Microns.
Microns, exactly. Did you know that microns is actually a unit of pressure,
yeah.
right? So a micron is, how many have heard of measuring a vacuum in mercury? A mercury vacuum? Sometimes you'll see it in it's mmHg, right? It's millimeters of mercury. A lot of times when you're looking at your weather app, you'll measure barometric pressure in bars of mercury. So you can measure a vacuum in mercury, but the problem is when you start to get really low and really small, the amount is just so tiny that it doesn't show up on your scale. So we use microns, which is actually it's 10 to the negative sixth of a bar of mercury, right? It's lots of zeros.
How do you have that memorized?
Because it's a micron. It's measuring.
Oh, so it's literally in the tens.
It's 10 to the negative 6. It's 10 to the negative 6 power. Just like a millimeter would be 10 to the negative third power.
Okay, that's cool.
Yeah, so a micron, it's just a smaller scale that allows us to measure that vacuum more accurately, because when we're doing vacuum, right, we're trying, certain things happen at different levels of vacuum, right? We're trying to evacuate our system, so I want to get below a certain number, and I need a scale that lets me measure that accurately. That's what micron is. When we're measuring air pressure, static pressure in our ductwork and stuff like that, we use another one called inches of water column, right? Which is it's still pressure, but we're measuring it using a different scale that lets us
Got him. Hey, what tool do we use to measure our air pressure in HVAC?
Gauges.
Nope. Nope. Gauges show us PSI, and the air pressure.
said it.
That's the guy. I have a couple different manometers in my hand. This is the wireless field piece one, and then this will give me a digital display on my phone. This is the older analog. So this analog is not the same as this analog, right? The spring in here is much more sensitive. So it's giving me it's picking up a much more sensitive air pressure. So if you think about, if I were to put this into the return or supply, I'm not gonna get a PSI reading. The air pressure pushing on the ductwork, it's still pressure, it's forcing against the edges of the ductwork. When you pull the panels off and it fights you, or you put it on and it slaps on, that's the pressure you're feeling that the airflow is creating. But it's not enough to be measured in PSI, not even 1 PSI. So we go down to a different measurements, inches and water column. And so if you look at this, like I can take this and blow on it. Took it all the way up to 35, but I don't think I can move this. I couldn't move it, so. Yeah, but, so that we do have a few different pressures that are not on this slide, that we do work with.
I think I put a note for like pascals and, yeah.
But it's more important that you understand that our 3 main that we're gonna be working with, we're gonna be measuring air pressure, which is
Inches of water column.
inches of water column. Good job, Elliot.
Oh, sorry.
We're going to be measuring our refrigerant pressure, which is
PSI.
PSI, and we're gonna be measuring a vacuum pressure, which is microns. Nice.
Awesome.
Cool. Those are the 3 that you need practically to remember.
Okay, so moving on to temperature. This is my jokey poke at Brian, because this is the scientific definition of temperature, right? Which, yeah, I'm not gonna read this one. I'll read it later one because they're more fun. But yeah, it looks like kind of gibberish, right?
Temperature is a measure of the average molecular velocity given a substance, is measured in one of many arbitrary scales, including Celsius, Fahrenheit, Kelvin. I don't know who he is. It is not equivalent to the amount of energy in a thermodynamic system and is considered intensive property of matter rather than extensive.
So everybody got that, right?
Intensive,
Intensive.
that's your key word there.
Yeah, not extensive.
Yeah.
Okay.
Great.
What's temperature really? So, temperature is a measurement of average molecular velocity, right? That part we're gonna keep. What that means is, how fast is it moving, right? The faster something's moving, the higher its temperature is gonna be, right? The slower it's moving, the less its temperature is gonna be. So if I have the molecules in an ice cube, they're not moving very much, right? They're moving pretty slow. It has a low temperature. But if I boil that, right, all of a sudden my molecules are bouncing all over the place, they're moving really fast, they have a high speed, high velocity, high temperature. That's what I'm going to take away from this. But the other thing is that temperature is not the same thing as heat. So this is going to break your brains a little bit, but in our world, something can be cold to the touch and still have heat, right? Heat energy is not the same thing as temperature. You think of an ice cube as cold, right? But there's no such thing as cold. There is the absence of heat, right? That ice cube still has heat energy in it that we can measure. We just don't think about that with our brains. But when in our trade, right, you get into HVAC, I grab a suction line that has a measurement of superheat on it, but I touch it and it feels ice cold, right? Well, how can that be? Because we're not talking about temperature, we're talking about heat energy, right? So those two things are not the same. And we use different measurements to calculate those, right? So we'll still use Fahrenheit for our temperature probes and everything like that, and that we do need to know that temperature because it is important, but it is not the same thing as how much heat something has.
And so when we are cooling a house or a building, some sort of space, we're moving heat, not temperature. And so that's important. We actually can we can manipulate temperature, we can control things with temperature, but what needs to move is the heat. What needs to come out of the space is energy. And so we have to somehow manipulate energy to get it out. And so if you guys, everyone jump up and grab that suction line. So here it is, it's the bigger one. Come over and grab it. What does your body tell you about it? Listen to your body. Adam says it's beer can cold.
Beer can cold.
And he's right. Nice. I was wanting you guys to guess its temperature.
Yes.
Here we go again. Now we're going to touch it again. A little more intentionality. So when you have testing in mind, you're going to do things a little bit more intentional, right?
In the 50s?
Okay.
35 maybe?
35, the guy says.
Like 46.
40.
46. You just guessed. Did you touch it?
Yeah.
What?
Yeah, I mean, how many times have I touched the suction level?
So many times have I touched. He's like, I'm done with this. I'm done with touching suction. I was like, 46. 46? Really? It feels cold. Is it 46?
All right. So we got 46. We got 50. We got 35. What else?
60.
40. Anybody else? Come on.
Oh, easy.
Let's get brave.
It's negative 60.
I'm going to touch it. I don't want to touch it. 72 in here?
I was gonna say, I can calculate it, what it should be.
That'd be cheating. I must be. I'm just trying to get a feel for how warm this is compared to this.
What, 35?
56 feels like it should be warm for how it should be operating. But my body tells me 56. But should we listen to our body? All right, there it is up there. What does it say the suction is?
73.6.
Yeah, well, it's not. We're about to find out. Here we go.
52.
Oh, snap. Oh my gosh, it's way colder than I thought it was.
Yeah, I was gonna say, it's.
What'd I say, 46? Oh.
You can say whatever you said. You can say whatever you want. Adam was close to 50. Anybody was in the 40s?
Yeah.
Yeah,
Not just in 40.
that's right. Nice, guys. Right on. So only about 3 of us can rely on our bodies. Perfect accuracy of measurement. And the rest of us will go like this. All right, so the point is, in this, is that that line that is so cold, that line that is so cold is carrying all the heat that was removed from this space. Right? Everyone who in here already understood that that line is carrying all of the heat that it removed from the space? No?
Yeah.
Who understands?
Who already knew before I made that statement who already understood that that line is carrying all the heat that was in this space.
Right.
Cool, let's talk about it for a little bit then, because it's one of the funnest things in the whole world. If we slide over to our return and supply, they're still stabilizing. We have our supply dB and our return dB.
Does anybody even know what that stands for?
I'm gonna pick someone who doesn't know.
Sorry. No, you're good.
Kieran, do you know why they have WB and dB on here? Two different measurements of temperature? Good, excellent. Glad we don't. Alfonso, do you know why?
It would be our wet bulb and our dry bulb.
Yeah, okay, and so then what is a wet bulb temperature? What is it?
That would be
It includes the
moisture.
humidity, right?
It includes the humidity, yeah, it accounts for moisture. Excellent. Yeah, so if you think of an old temperature probe, just sitting in your counter, and it has the bulb and the red mercury inside. If you take that bulb and you make it wet, and then the air comes across it and that evaporates, it'll cool that down. And so that temperature that it comes down when it's wet is what we call wet bulb. And we can use that to then calculate how much relative humidity, how much moisture content is our air holding. So wet bulb in itself isn't something you guys can use, but you use it to do some other form of calculation. I need to find out where to set my superheat. I need to find out what my humidity is. Thankfully, we have things like apps doing the math for us and telling us what the humidity is. Because I have no clue how to do that math, what the equation is there. But let's not get lost in trying to figure that out. All right, so we have a supply temperature of, what is it? What's our supply temperature?
Dry bulb. Anyone?
51.
Man, you guys are so blind. 51. Yeah, and our return 68. Nice. So we got a split of 17 and a half. Yeah, that's kind of low. We were noticing that yesterday. This thing's moving, it's a 3-ton, it's moving about 1050 CFM, 1050
Yeah.
CFM. So, and that air that passed through there dropped 17 degrees. It gave up its heat. And all that heat that it got rid of was in the line you were touching. So
CFM is
it's
just
loaded.
Sorry, CFM is cubic feet per minute. It's just it's a measurement of volume of air, how much air we're moving through there. Yeah.
So we take a foot and we move it across that unit in 1 minute. Foot of air. But we take 1,050 feet of air and move it across that unit in 1 minute. The air's moving a little faster. And if you want to know how fast it is, just put your hand in there and feel how fast that is. But yeah, it's kind of fun. So back to what Elliot said here, this is crucial. We have, what was that suction? Now 47? It was 56 right before I tested it. Temperature is not heat. So we have moved the heat out of our air in here and put it in that suction line that is really cold to touch. What's going to happen to that heat next? Let's go back to
It's
here.
gonna be expelled, or it's gonna be compressed.
Before it gets expelled, it gets compressed. Yeah. So our heat came out on our suction line, still loaded with heat, but it gets smashed, right? And then what happens to that heat?
Rise in temperature.
Exactly. We manipulate its temperature. That's what the compressor does. It's the same heat, but now it's maybe 140 degrees.
We're going to cover all this more in depth because we're
Yeah.
getting a little ahead of ourselves, but
So now it's maybe 140 degrees, but it's the same heat. And that's what you need to take away from this. The same heat can be 47 degrees or 140, same heat.
So that's gonna, and the reason we need to increase the temperature is for what we're gonna segue into now, which is the second law of thermodynamics, which again, this one's fun. The second law of thermodynamics is a physical law based on universal empirical observations concerning heat and energy interconversions, and states that when energy moves from one form to another, or when matter is allowed to move freely, entropy increases. So what that actually means is that hot and cold, wherever you have something that's hot, it's gonna move to something cold, right? If I take something that's 90 degrees, right, and I take something that's 40 degrees, then the 90 degrees is going to decrease in temperature, and my 40 is going to raise in temperature until they find this point called thermal equilibrium, right, where the two things meet. Everything ends up at the same, right? If I put an ice cube in a glass of water, that ice cube is going to melt, right, until it reaches the same temperature of the water, and everything's all one temperature. Nature loves a balance, right? Everything wants to move from high to low. You see it with pressure, you see it with heat energy, right? And so that's what this law is telling us. So the reason that we can move the heat around and make it go where we want is because it wants to find the balance point. So when we are using our compressor to increase the temperature, we're increasing it so that it's hotter than the outside air, so that it will then give up that heat energy to the air, trying to find that balance point.
Yeah,
Cool?
that's good. And this is absolutely crucial for how the AC works, because why?
I mean, that's how you're creating like the cooling, heating effect is like heat transfer.
That phrase right there, heat
Yeah.
transfer.
Heat transfer.
That's what we're in the business of doing, is moving heat,
We don't, I think, is it the next?
but probably.
Yeah.
But we can't be doing that unless we manipulate its temperature, because we just learned, and hopefully most of us already knew, but the heat only moves when there's a temperature difference. So we already figured out we gotta get rid of energy, that's our job. We're not getting rid of temperature. We're not getting rid of a high temperature in a room, we're getting rid of energy, and that'll bring down the temperature. But in order to move energy, we have to put extreme temperature differences together. And the energy always moves from the hotter towards the colder. It will move.
And it's, the way it works is there's a little bit of diminishing return. The greater the imbalance, the faster it will move at first, but the closer they actually get to that center point, the slower it moves. So if I have, 100 degrees and 50 degrees, they're gonna move much faster toward that center point than if I had 40 degrees and 50 degrees trying to move toward 45, right? They'll both get there eventually, but it takes a lot more time for that little bit of change.
That's good. Because if our air inside, let's say it's 78, and it's coming into our AC system, and our coil is 77, there's gonna be heat transfer into that coil. It's 1 degree difference, there'll be heat transfer. But it's not gonna be much. It's gonna move very slowly, it's gonna be very inefficient. So you will have heat transfer, but the colder you can get the coil, the faster the heat will move from 78 to 40. We're creating a much stronger pull. We're two different energy levels, and the greater that you push those differences apart, the faster they want to move together. So the magic of AC is that we get this coil as cold as we can without putting it in a range of freezing danger, so that when our air comes across it, it releases its heat fast. We could keep the coil at 60 and it would remove heat from our 75 degree air. But when our coil is about 35 degrees colder than the air, that's when we get around our 20 degree perfect split on our system. Air comes out 20 degrees. It moves heat pretty fast and efficient. About 35 degrees is what the target is, what we're aiming at.
Yeah, it's a balancing act between our refrigerant circuit and the airflow, and
Yeah, it would be nice if we could make it 19 degrees.
no, because then we can do it really fast. But
Nice. It'd be nice if we could keep it at 36. But conditions change, filter gets dirty, it starts raining outside, refrigerant levels change. What was 36 today is now 28 on a different day, and it freezes. So we bring that balance point up closer to the 40s. Most of the time our coils are in the 40s is far as temperature wise.
And because you can't keep it colder than that. So if you guys in commercial ever get into like refrigeration, you see like the freezer cases, right? Those coils are kept at below freezing, but you have to run a defrost cycle periodically because you will form ice. So yeah, but what we're doing, what the HVAC equipment's job is we're creating imbalances in temperature so that we can get it to move where we want it to. We're not, you'll talk to some homeowners and like, oh, you know, the Freon's making cold, right? That's not a thing. We don't make cold. We move heat from inside the house to outside the house, and we're using just natural laws to make that happen. We're creating an imbalance so that it will try and find that center point, that happy place, and we use our compressor to do that. We use our metering device to manipulate those.
What's another thing other than refrigerant that and temperature that we work with constantly in our trade that runs off the same principle of energy imbalance?
Electricity.
Yeah, exactly right. If you pull out a meter and you take the two prongs, you stick it on. Basically, these two things are measuring not what the electricity is. That's right. Good. The difference. It's measuring the difference between two energy points. I could have 1,000 volts on this Apple TV, and if I take my leads from one side of the Apple TV to the other, what will my meter show me? Zero. It'll show me 0 because this measures two different points of energy. But if I go from my Apple TV to ground, that's where it shows my 1,000. Because now there is a difference between energy and these 2 points. So your meter is only showing you what's the difference between energy, electrical energy, between these two areas. And that's why a lot of people say that instead, a lot of people training or classroom conversation, you'll hear potential difference. What's the potential difference in my voltage? Because it's not actually flowing at that point, it's just you're touching 2 points. There's a potential for this much electricity energy between these 2 points. Now we got to create a path. We put something in between it that lets electricity actually travel, and that electricity moves really fast. It's an incredible amount of energy.
Like lightning.
It moves lightning fast, literally. So,
this is why we always, when we do our safety check, you guys are checking power, check it to ground. We don't check it to other circuits, we check to ground because that'll tell, we are ground. So we're looking for the potential difference between whatever I'm about to put my finger on and whatever ground is. And if there's a difference, then I'm gonna get that.
yeah.
Make sense?
And when we are checking equipment to see if it's operating the way it should, we're not using ground as our reference. Equipment operates between on low voltage or hot and common, or on high voltage our lines of power coming in. So we're checking between our lines, and we're checking between our hot and common on low voltage in order to know if we have our proper voltage. That's for diagnostic, which is different than safety. Many times you'll experience going and checking voltage and it'll show you 0 volts, and if you touch it, you'll get shocked. You have one leg of power coming through the equipment and back on the other side. So when you touched your 2 lugs, it was the same power. There was 0 difference between the 2 points. But to ground, there was a big difference. So that's why safety is always to ground, but diagnostic isn't.
Cool.
Same principle. Energy wants to equalize.
So we know that we need to create some imbalances in our temperature in order to get the heat to move where we want it to move. So let's look at ideal gas laws next. So this is another one. You want to read this one?
I was hoping Manny could read this one.
Manny, read it for me.
The ideal gas law, PV, equals nRT. Say that pressure times volume is equal to the moles of gas present times the temperature times the molar equivalent of the Boltzmann constant. Furthermore, Gay-Lussac's law states that for fixed volume and quantity of gas, pressure and temperature are directly proportional.
Cool, awesome. Everybody get that?
Yeah.
I got it.
I mean, yeah.
Well, the last class we did, I learned that this principle was called the ideal gas law.
Yeah, even we're still learning.
10
so-
years in,
Yeah,
I learned that that's what it was called.
so it's always okay to not know something. It's just not okay to continue not knowing something.
Yeah, once you know don't know what you don't know.
So this is the law that tells us what Adam was talking about earlier about pressure and temperature being related. So because of this, so the P, let's see. Mark. Okay, P is pressure, V is volume, is equal to blah constant, another constant, and temperature, right? So I got an equal sign here. This will equal this, right? I don't care about volume because my volume is fixed. I don't care about these stupid constants because they don't matter to me. What I care about is pressure is equal to temperature, right? So if I change one thing, in order for the universe to not explode, this has to change too, right? Because we're on either side of an equal sign, right? So if I increase pressure, my temperature has to increase. If I decrease pressure, my temperature has to decrease, because this will always be true. So if I have a pressure, am I getting ahead of myself? No. So basically I have to, if I increase the pressure, I'm going to increase the temperature. That's what the compressor does. If I want to get the temperature of my refrigerant that is, was it 48 now, right? Mm-hmm. That suction line is 48 degrees, but I want it to be hot enough to where it wants to find balance with the outside air. It's like 80 degrees outside, right? So I need to get my refrigerant temperature up to about 95 degrees or so. Well, how do I do that? I'm not going to light a fire under it and add heat energy to it, because that's not how we do things. That's going to be really inefficient.
I'm trying to remove heat.
Exactly, I'm trying to remove heat from it. What I can do though is I can change the pressure. So if I compress that, if I increase the pressure with my compressor, then I'm going to drive the pressure up, and that has to drive up the temperature. What?
Pointing to the wrong side.
You got rid of my equation.
Yeah, I just realized that it was so unuseful.
Oh.
Yeah, we're here to teach practical
It was
stuff.
so unuseful.
So,
but what is more useful is if you point right here and say the same thing.
okay, so my compressor will drive up my pressure, which necessarily increases the temperature. So when I move to my condenser, I am now hotter in here than I am out here, and that heat will transfer.
Yeah. That's good. That's great. I'm going to do a little drawing to demonstrate what he's talking about. And don't be angry at me, and don't move our slides yet.
I don't know what
Because
to do
they're
next. I don't know what's coming next.
I just don't like you writing things that I can understand. I think that makes me feel insecure. That's right. Which is a great feeling.
So what I have on the slide is kind of showing you so why does increasing pressure increase temperature? Well, we said earlier that temperature is a measure of average molecular velocity, right? So if I've got little balls that are bouncing around in the room, right, and they have all this room to move around in, if I close in the walls, they're going to start hitting walls faster and bouncing faster, right? So I didn't change how much heat energy I had, but they are moving faster. And since temperature is a measure of the speed of the molecules, my temperature is now increased.
So we have 48 degrees loaded with heat energy that we need to get rid of. We get rid of that energy right here in this space. But if we take 48 degrees and just pipe it straight to the getting rid of place, then 48 degrees is going to go around in our coils, and our 80-degree air coming into those coils, it's not going to get rid of the heat in there. Even though it's loaded with heat, heat only moves in one direction, from hotter towards the colder. So the heat in the air is actually going to just increase the heat content of that 40-degree refrigerant. And so instead of putting it straight to our condenser, we're going to smash it. We're going to take 40 degrees and we're going to make it,
95.
Huh?
95.
95?
For 80 degree air?
We're going to make it 95.
2 degrees above ambient?
Yeah. And, no, actually, on discharge, I'm talking about the discharge.
Oh, okay.
Let's do 130.
Gotcha.
We're going to make it 130, now it's well above 80 degrees. That same heat.
Okay, so yeah, to reject heat, the refrigerant must be hotter than the outdoor temperature. So the compressor's job is to raise the temperature by ramping up the pressure. The compressor does not add any heat energy to the refrigerant, right? Footnote. a tiny amount, but not practical for what we're doing.
Its job is not to add heat.
Its job is not to add heat. I could have sworn I had that in there.
No, I asked you not to because I didn't want them to even know about it.
Oh, I'm sorry.
That's-
Forget what I said.
It's distracting.
The compressor does
It's
not add
distracting.
heat.
So the compressor is cooled the electronics of the compressor is cooled by the refrigerant. So the electronics do get hot as the motor's moving, so it adds heat, but we wish it didn't. It does add a little bit of heat from that motor, but the job of it is to increase the temperature, not to add heat.
And so so it increases the pressure, which necessarily increases the temperature. Now I'm hotter than my outdoor air, I can reject the heat, right? That same heat that I just took out of the house, I can now reject outside. The metering device is the complement to this. This is the pressure dropper, and it does the same thing. So I've got this refrigerant coming into my metering device that is now closer to what the outdoor air temperature is, but I need it to be colder than the room that it's, the room air, so that way I can now absorb heat. So I need to do the same thing. I need to change my temperature of the refrigerant. How am I gonna do that? I'm gonna play with the pressure again. My metering device will now drop the pressure so that it will be a lower temperature than the air that's in the room, and now I can absorb heat again, right? So I haven't changed anything again as far as heat energy that's in my refrigerant. I'm manipulating the temperature by changing the pressure so that I can now transfer heat again. So this is my pressure increaser, this is my pressure dropper, right? They're the ones that are creating the imbalance that allows us to use those natural laws to move the heat energy.
I want to hang out here just
Yeah,
a
me
little
too.
bit because it's so important for
Yeah,
our trade.
this is the magic of HVAC.
Thanks for watching. If you're willing, give this video a thumbs up and drop us a comment. Don't forget to hit that bell icon to stay updated with all of our future videos. And as a quick reminder, HVAC School isn't just a YouTube channel. Dive deeper with us at our main website, hvacrschool.com. Curious for more knowledge on the go? We've got you covered. Tune into the HVAC School podcast, available on all your favorite podcast apps. And while you're at it, join our thriving Facebook group. Also, don't miss out on our free mobile applications available for both iPhone and Android. We're all about community. For techs, by techs.